All right, we've got a number of problems here from section 6.6, which is solving exponential and logarithmic equations, certainly one of the more important sections in this chapter here. So for our exponential equations, one of the things that I can see, at least in this first one, is that we can have our bases alike. And anytime we can set our bases equal to each other, that's what we want to do. So 6 obviously is, we're going to leave, but 1 over 216 is the same as 216 to the negative 1. And then 216 is 6 cubed. So we have 6 cubed to the negative 1. Power to a power, we're going to multiply. So that's 6 to the negative 3. Now we can set our exponents equal to each other. And n is equal to negative 1. Okay, moving on. 81 and 343, I'm going to write in base 3. So 81 is 3 to the 4th. That's raised to the negative 3r. 343 is 3 to the 5th. Again, power raised to a power will multiply. Negative 12r equals 3 to the 5th. Set our exponents equal to each other. And we get negative 5/12. Down here, we're going to use 5 as our common base. So 625 is 5 to the 4th. 125 is 5 to the 3rd. Again, power raised to a power. 5 to the negative 8n equals 5 to the negative 3n. Set those equal to each other. Add 3n, we get negative 5n equals 0. N is equal to 0. Next one, I see that I've got some operations to do along with our different exponents. So I'm looking at 4, 16, and 32. And I know all of those could be written in base 2. So I'm going to first rewrite them. So 1/4 is 2 to the negative 2. 16 is 2 to the 4th. And 1 over 32 is 2 to the negative 5. So again, all of these are power to a power. So we get 2 to the negative 4k times 2 to the negative 12k equals 2 to the negative 15k plus 10, right? Power to a power. And because we're multiplying like bases, we can add the exponents. So over here we have 2 to the negative 16k. 2 to the negative 15k plus 10. So now that I've gotten down to 2, one term on each side with like bases, we're going to set the exponents equal to each other. Going to add 15k to both sides. And k is equal to negative 10. Okay, let's move on. So again, similar problem here. But I'm going to leave this in 25 because I know that 625 is 25 to the 4th. So we have 25 to the 3n plus 3 times 25 to the 1st equals 25 to the negative 2 because 25 squared is 625. So again, on the left side, we're going to add our exponents because we're multiplying like bases. So 3n plus 4 equals 25 to the negative 2. Set our exponents equal to each other. 3n equals negative 6. N is negative 2. Again, I have 64, 4, and 32. So I'm going to use base 2. So 64 is 2 to the 6th. 4 is 2 squared. And 32 is 2 to the 5th. So again, power to a power will multiply. So I get 12 minus 18v. Here we get 4v minus 4. I'm sorry, 6v, not 4. Equals 2 to the negative 5v minus 5. So here, notice we're dividing this time. We're dividing like bases, so we're going to subtract our exponents. So we have 12 minus 18v minus 6v minus 4, and that will end up equaling the negative 5v minus 5. So 12 minus a negative 4 is plus 4, or 16. Negative 18 minus 6v is negative 24v. Equals negative 5v minus 5. I'm going to add 24v to both sides, and that'll give me 19v. Add 5, I get 21. So v is going to be 21 over 19. Okay, so now notice it's asking us to round to the nearest 10,000ths. We're just going to go to 3 decimal places. So no matter what, we're going to use that as our standard because that's what it will be on your AP exams. So first one I'm going to divide by negative 2. So I have 10 raised to the a plus 1 equals 11. So now again I have an exponential equation, but we're not going to be able to write the bases alike. We're not going to be able to write 10 and 11 using the same base. So I'm going to use logarithms. So I'm going to take the log base 10 of both sides. I don't have to write 10, right, because it's understood. So applying the power rule, we have a plus 1, and the log of 10 is 1. So that equals the log of 11. So a equals the log of 11 minus 1. So again, we're going to go to our calculators because we're approximating. So the log of 11 minus 1, a will be 0.041. And we can just leave it as that. Again, that's our 3rd decimal place. Okay, moving on to the next one, it's base E. We're going to add 5 to both sides first. And because we're base E, I'm going to take the natural log of both sides. So we get x plus 2 times the natural log of E, which is 1, which is why I'm using natural log this case. So x equals the natural log of 76 minus 2. Again, that should have been an approximation down there. So now we'll go natural log of 76 minus 2 and 2.331 rounding to that 3rd decimal place. Okay, moving quite along, we've got one more here of our exponentials. So I'm going to divide by negative 1 first. So 20 to the 9r equals 21.7. So we're not in base 10 or base E, so we do have to take the log both sides, and you can choose. I'm going to use natural log. So using our power rule, I have 9r. Now the natural log, this is not E, so it's not 1, so we need to keep that. So I'm going to divide both sides by 9 times the natural log of 20. That's 1, that's 1. And again, using that on our calculators, parentheses, natural log of 21.7 divided by, and then our parentheses, 9 times the natural log of 20. And we get 0.114. Okay, now we're going to move into some log equations. And we have the same base, so we can, similar to with our exponential equations, at this point we can set our our arguments rather equal to each other. So I add 4v, I get 7v equals 0, v equals 0. But remember, the domain of a log function is that the argument has to be greater than 0. And so if I substitute 0, we'd be taking the log of 0. So for this one, there is no solution. Okay, here again, we have the same base, so we can set our arguments equal to each other. So k squared plus 1 equals 9k plus 1. Our quadratic, we're going to set it equal to 0, so I'm going to subtract 9k and subtract 1. Quadratic binomial, I'm going to factor a k out of both terms. So we get k equals 0, k equals 9. And if I substitute 0 back in, that actually works because we'd have the log base 5 of 1 on both sides. And if we substitute 9, we end up with the log base 5 of 82 on both sides. So both answers work. There's no extraneous solutions there. All right, a few more. So again, we have another log. We're going to isolate that log statement. So I will subtract 8 from both sides. We get -3. Divide both sides by -3. Log base 5 of 10 minus 2x equals 1. So now, because we don't have a log statement on the other side, we're going to write this as an exponential. So 5 raised to the first equals 10 minus 2x. Subtract 5 from both sides. -5 equals -2x. X is 5/2. And again, we do want to check our answers. I'm not going to go through that, but I do know that this works. All right, we have log statements all around here. We have a sum, so we're going to apply our product rule. So that means we can multiply. So now that we've got one log statement on both sides, we set our arguments equal to each other. And I'll distribute that, so I get 5x plus 40 equals 47. Subtract 40, divide by 5, and we get 7/5. Here we're subtracting, so we're going to apply the quotient rule. So the log base 5 of -x over 9 equals 1. Again, 5 to the first equals -x over 9. Multiply both sides by 9, and then x equals -45. And note if I substitute -45 back in for x, we do have minus, so minus a minus, that'll be a positive, so -45 is a solution. Again, another one where we're subtracting, so we're going to apply our quotient rule. Again, rewriting this as an exponential, 2 to the first equals x squared plus 2 over 9. Multiply both sides by 9, we get 18 equals x squared plus 2. Subtract 2, square root. There's that absolute value again, right? We've talked about that many times this year, one of the more important topics. And we get both plus or minus 4. And both of them, if I plug them back in, make the equation true. So you've seen lots of exponential and logarithmic equation solving here. I hope that helps, and we'll see you soon.